St. Jude is a very special children's research hospital. It was one of the first in the world dedicated to children's cancer in the middle of the last century. And the vision that the founder of St. Jude laid out for us was that we should arrive at a world where no child will die in the dawn of life. And to able to achieve this mission, we are focusing on two different activities. One is that we are focusing on the treatment of cancer patients. And the other one is that we are trying to find new cures for cancer. Now, St. Jude is one of the biggest charities in the US, getting over $1 billion each year in donations. And this allows us to do really special things in both these different areas. And to mention a few examples, regarding the treatment of patients and families will never receive any bill, not for treatment, not for food, even if you don't have a health insurance. As an example on the research side, a few years ago, St. Jude obtained the world's most powerful superconducting magnet. And this allows us to look more deeply into atoms and molecules than ever before. Another very special thing that St. Jude has done a few years ago was to partner with SpaceX for the first all-civilian mission into space. So 4 astronauts, 3 days around the Earth with a Falcon 9 rocket. And one of the astronauts was Haley. And Haley, she had cancer, and she was treated at St. Jude when she was a child. And she survived, and she loved St. Jude so much that she joined us later as a physician assistant and is now a very dear colleague of mine. In this mission, Haley represented the quality of hope. And another thing, technology which gives us a lot of hope for the future for curing cancer is quantum computing. And this is why right now we are already engaging in quantum computing research. Regarding the remainder of the talk, I will talk about a novel hybrid quantum classical algorithm for drug discovery that we helped to develop, and then its application to a real cancer drug target. The drug development process, as many of you will know, is very time-consuming and expensive. A single successful drug on average costs $2.6 billion and takes 10 to 12 years in development time on average. Now, one of the early stages of the drug development process is the initial hit and lead identification step. And this is the step we have focused on in this project. So in most diseases, it is proteins which play a central role. And what one needs to do in order to find a cure is to find another molecule which binds to the target protein of interest to modify its function. But one class of molecules or ligands binding to proteins are small molecules. And an example you can see here on the right side. But to find a suitable small molecule for a given target site and target protein, it's a daunting task. One reason for that is that the chemical space of small molecules suitable for drug discovery is extremely large. It's estimated to contain more than 10 to the power of 60 molecules. And just as in comparison, our Milky Way galaxy roughly contains the same number of atoms. Now, traditional screening methods, such as experimental high-throughput screens, they are only able to screen or look at a very tiny fraction of this entire chemical space. But one promising approach to explore this entire chemical space here is to use like machine learning and generative models. And quantum machine learning models might have an advantage compared to classical machine learning models in exploring this space. So and this is the approach we have focused on in this project. And for that, we have joined an amazing team with the group of Alina Spor-Gussig in Toronto, in silico medicine, Zapata Computing, and a group in Stanford University. And I would like to highlight in particular Mohammad, who has been a lead person in this project. Now, our approach is a generative model which combines both classical and quantum computing. And it requires training data. So this is the first step in our approach. And once we have obtained the training data, then we can train our new quantum classical algorithm. And once it's trained, then we can really apply it to real application and validation studies. So let's look a little bit more closely at the first step, the training data generation. Training data here means that for the target protein of interest, that we need to have some small molecules which are expected to bind to that target protein. And I'm highlighting now 3 different approaches which we used later in our project to obtain the relevant training data. One approach is to use experimentally known ligands. And this can be done, for instance, by data mining the literature and patents. Once one has identified some of these experimental ligands, one can do a process called hit expansion. That means finding or generating very similar ligands of these experimental ligands. And the algorithm that we have used is the stoned algorithm. And the stoned algorithm, it was developed by one of our team members, Akshat, prior to this study. It is based on interpolation and extrapolation between molecules using a string representation. And this completely bypasses the need for training a generative model to generate similar molecules. A third approach that we have taken to generate training data was to carry out ultra-large virtual screenings using the Virtual Flow platform. So Virtual Flow is a platform that I have developed several years ago, and it was the first platform that was able to screen billions of small molecules against any given target protein. The first version was published in Nature in 2020. Here you can see an overview of the platform. Here at the top, this is the ligand preparation module of Virtual Flow, and at the bottom, VFVS is the virtual screening module of Virtual Flow. Earlier this year, we have completed the second generation of Virtual Flow 2.0, and it has many new advanced features. For instance, it provides a 69 billion molecule library with commercially available ligands, and this in a ready-to-dock format. And this is the largest library in the world available to date. But it also has many other advanced features, such as also support for the AI and ML communities, who also develop other machine learning tools for drug discovery. Once all the training data was generated from these different sources, they can be merged together to form the entire set of training molecules. And these molecules can then be used for training our quantum classical algorithm. So now, how does our quantum classical algorithm actually look like? It consists of 3 key components. The first one is a QCBM, a quantum circuit-borne machine, and it is used as the prior distribution for an LSTM model, which actually generates the new molecules. And the third component is a reward function and a filter, which assesses how good these molecules which were generated really are. And this entire cycle, it's a closed-loop iteration cycle. And once the training is complete, it can be then used to generate new molecules. The QCBM can be run on the quantum computer, such as IBM's. And the other 2 components, the LSTM and the filter, they are run on classical computers. Here on the left, you can see again the iteration cycle. And on the right, you can see it expanded in more detail. And the colors on the right match the colors on the left, so you know which component belongs to which part. Now, one very important component was the QCBM. A QCBM, a quantum circuit-borne machine, is a generative quantum machine learning model. And it contains a parameterized quantum circuit, which is optimized by gradient descent. So it's a special case of a variational quantum algorithm. And it uses the Born rule to generate complex probability distributions. The QCBM was first developed by Liu and Wang in 2018 and was subsequently implemented by the Zapata Zapata computing in the Orchestra platform. Orchestra is an quantum and AI based software platform. And the team from Zapata was so kind to provide us with an open source version of their QCBM. Another component here which I want to highlight is Chemistry 42. Chemistry 42 is, it was used here in conjunction with our reward function and filter. And it is an AI platform for generative drug design, which was developed by In Silico Medicine. It contains both generative algorithms for molecular design and also advanced reward functions, which can include and account for many molecular properties which are relevant in drug discovery. We only used the reward function part of Chemistry 42, since we had our own generative model enhanced by, containing the QCBM and the LSTM. So much to the quantum classical algorithm. Once it is trained, then we can really use it for application and validation studies. And this is exactly what we have done. And at St. Jude, as you already know, we are interested mostly in cancer. So we have chosen a heavyweight target in cancer. It's called KRAS, and it's sometimes also called the Death Star of cancer because of its key function in many types of cancer. Cancer is still one of the leading causes of death, and KRAS is one of the most mutated oncogenes in cancer. Historically, it was considered to be undruggable because it's really difficult to find small molecules binding to the surface of that protein because it's quite flat outside and also because some parts are quite dynamic, so moving a lot. But a few years ago, there was the first real success stories for KRAS, and the first drugs appeared on the market for the KRAS G12C mutant. However, the G12C mutant, it's not a very common mutant. The most common mutation of KRAS is the G12D mutation. And for that one, no drugs exist yet on the market. And this is the one we have focused here in our application. Regarding the training data generation, we used all these three different approaches which I mentioned before. And our data mining approach has yielded 650 molecules. We then used the Stone algorithm to generate around 850,000 similar molecules. And then we used virtual flow to screen the 69 billion molecule library. And then we took the top 250,000 molecules for training. So in total, it was a little bit more than 1 million molecules for training. We then used this training data to train our hybrid quantum classical algorithm. And then we did two types of studies to evaluate the performance of the model. The first one focused on the filter and reward function. And here we looked at the success rate of molecules passing through the filter. So the success rate is basically the number of molecules that pass divided by the number of molecules, the total number of molecules tested. And what we did was we not only run our algorithm using a real quantum computer from IBM with 16 qubits, we also used as an alternative model, we run it on a quantum simulator. And then we also swapped out the QCBM with a multi-QCBM just to compare the performance. And then we also removed the QCBM completely and replaced it with a classical prior distribution to be able to compare the performance of this quantum enhanced model with a pure similar classical model. And regarding the success rates, in blue you can see the three quantum models which I just mentioned. And in gray there is the classical LSTM. And as we can see, the success rate is around 10 to 20% higher for the quantum models. We then, and this used a local filter and reward function which we run on our own computers. And then we did the same benchmark again using Chemistry 42 as the reward function and filter. And again, also in this case, the quantum models outperformed the classical LSTM. As another validation, we selected some molecules for real synthesization and then experimental validation whether they really bind to KRAS. So for each of these 3 different batches, the classical approach with the classical LSTM, the quantum approach run on a hardware, and the quantum approach run on a simulator, we selected around 10 molecules for each of these approaches. And the selection procedure included different criteria, and here we used mostly Chemistry 42 platform from In Silico Medicine. And what we then did is we tested the binding of these molecules. So the first thing we did was, we used a CRO to synthesize these molecules, and then we used SPR to test these molecules for their binding ability to KRAS. And this is still work in progress, so I can only give you like a preview on the results. And so far we have synthesized 15 of these 30 molecules, 8 from the quantum hardware batch, 4 from the quantum simulator batch, and 3 from the classical LSTM batch. And out of these 8 compounds from the quantum hardware approach, 3 compounds have shown to really bind to KRAS. And 2 compounds out of the 4 compounds from the quantum simulator approach also have shown real binding to KRAS. And regarding the classical LSTM approach, 1 out of the 3 compounds has shown binding. Of course, this is a very small sample size yet, and we cannot draw too many conclusions from that. But the strongest binding compounds, which from all the binders, are from the quantum batches. And another interesting observation which we observed was that the molecules generated by the quantum approach and by the classical approach are really different from each other. And these compounds can serve as also as starting points for further optimization. So in summary, we used a hybrid quantum classical generative approach and applied it to the KRAS G12D mutant. In benchmark studies, the quantum algorithm outperformed a similar classical algorithm. And even though this does not show quantum advantage, of course, it shows the potential that quantum computing has for the future. After all, we only used 16 qubits in this project. And it also shows that right now, quantum computers can already be used in a useful way in real-world drug discovery projects. And with that, I would like to acknowledge again the entire team, in particular Mohammad and Alan. And here is the contact information of all our groups which took part in the project. And we at St. Jude, we are also actively now looking for new collaborations on exciting drug discovery and structural biology projects. So if you are interested to collaborate with us, please feel free to reach out to me anytime. Thank you very much.